In this video, I'm going to talk about spontaneous processes and entropy, and in particular, we're going to talk about the second law of thermodynamics and how we can use that to determine whether or not a reaction is spontaneous or not. So the first thing we should probably do is define what it means for a reaction to be spontaneous. A spontaneous process is a reaction or a process that proceeds in a given direction without outside intervention. So you can get the process started, for example, lighting a match, and the reaction of burning the match will continue without any other intervention. So a non-spontaneous process is one that occurs only as long as energy is added to the system. So you can think of this as, for example, cooking an egg. Obviously, the egg needs a continuous input of energy from your stove in order for it to cook. So the spontaneity of a reaction depends on the dispersion of energy that occurs during a process. And we'll talk a little bit about that as we continue on through this section and throughout this chapter. So here's another example of a spontaneous process. If we had 1 atmosphere of a gas in the right side of this vessel and the other side had a vacuum in it, obviously we know what would happen if we open up this valve, right? The gas will distribute itself so it has equal pressures in either side of that vessel. And we didn't have to do anything for this to happen. All we had to do was open up that valve and the reaction or the process happened spontaneously. So this would be the spontaneous direction of this process. And the non-spontaneous direction would be if somehow that gas decided that it wanted to only occupy one side of that vessel. And obviously it's not going to do that by itself. We would have to supply energy and force it to do that. So that's why that process is not spontaneous. Another example is if you left your car out in the rain, it would spontaneously over time rust, whereas that rusty car would not spontaneously turn back into a nice shiny new car. So as I said before, spontaneous changes only need to be started, and then once started, they will continue on their own, whereas non-spontaneous changes need to be supplied with a continuous input of energy. Now, the one thing to remember about spontaneous reactions is that it has absolutely nothing to do with how fast a reaction will proceed. Spontaneous just means that the reaction will proceed in a specified direction, but it does not tell us anything about how fast that reaction or process will proceed in that direction. So how can we predict the direction of a change for unfamiliar situations? Right? It's pretty easy to do for familiar situations, but when we're looking at a reaction and trying to decide whether or not this reaction will proceed in a specific direction, how can we determine whether or not that will occur? So one question we can ask ourselves is, do these changes involve energy? And that is what the study of thermodynamics is, which is what this chapter is all about. So it's the study of heat and its transformations, the energy involved in a change, and the tendency of a reaction to occur spontaneously. So let's look at one thermodynamic property that you learned about in General Chemistry 1, and that is enthalpy or delta H. So it's true that many spontaneous processes are exothermic, right? So an exothermic reaction meaning that the delta H of that reaction is negative. So for example, combustion reactions are very exothermic and they are spontaneous processes. All you have to do is supply some heat, maybe in the form of a spark, and that reaction will continue on its own. But not all spontaneous reactions are exothermic. There are some that are endothermic. So an example of a process that is endothermic, that is spontaneous, would be the mixture of baking soda and vinegar to produce sodium ions, acetate ions, water, and carbon dioxide. That's an endothermic reaction, but it's also spontaneous. Another couple examples, if you have methane gas, it burns spontaneously through an exothermic process as shown in the chemical equation below. And ice melts spontaneously at room temperature, but this is an endothermic process. So the burning of methane releases energy, it's exothermic and spontaneous. The melting of ice consumes energy, it's endothermic, and it's also spontaneous. So again, you can see that in the value for the delta H, negative for the exothermic reaction, positive for the endothermic reaction. So what can we say about enthalpy and spontaneous reactions? Can we use enthalpy to predict whether a reaction is spontaneous or not? Well, as we've seen, reactions can be either exothermic or endothermic, and they can still be spontaneous. So the short answer to the question is enthalpy alone can't be used to predict whether or not a process is spontaneous or not. We need something else. So let's just look at one more example of an endothermic process that is spontaneous, and that is in the form of these cold packs. We'll also come back to this example a little bit later when we're talking about why this particular endothermic process is spontaneous. And the hint is in this diagram here. So in the initial state of the cold pack, it's usually filled with water and some isolated crystalline solid. These might be in some kind of plastic container so that it is not mixing with the water at that time. And then once that plastic container inside the cold pack is cracked, it allows the crystalline solid to dissolve in the water, producing these aqueous ions. That's the endothermic process, which results in that cold pack becoming cold. So there's something with the fact that we have a crystalline solid going to aqueous ions that allows this particular process to be spontaneous. And we'll start talking about that in the next couple of slides. So before we get there, let's talk a little bit about molecular motion and remind ourselves of what molecules can do when they're in specific physical states. So molecules have vibrational motions, they have translational motions, and they have rotational motions. So when they're in specific states, specific physical states like solids, liquids, and gases, they have varying degrees of these specific molecular motions. So in a solid, the molecules can't move around, so they don't have any translational motion. They can't really rotate because they're kind of stuck in place with the bonds and the intermolecular forces that are being used to hold them in place. So the only motion they have in the solid form is a vibrational motion. Now, in both the liquid and the gas states, molecules can move around, so they have translational motion, and they're also more free to rotate. Now, obviously, they'd be more free to move and rotate in the gas phase than they are in the liquid phase. So now let's talk about thermodynamic entropy, or S. So entropy is a measure of the distribution of energy in a system at a specific temperature. And you can think of this as the disorder of a system. So we can have a system that is very ordered, such as something that's in a crystalline form, or something that is very disordered, which would be, say, the same molecule that would be either in a liquid or a gas phase. So the second law of thermodynamics has to do with entropy, and it states that the total entropy of the universe increases in any spontaneous process. So the equation below, delta S of the universe equals delta S of the system plus delta S of the surroundings. So delta S of the system just refers to the entropy of the system, and we'll define that in a second. And the delta S of the surroundings corresponds to the entropy of everything that isn't the system. So what does it mean to be the system? Well, technically, the system is the part of the universe whose change we are going to measure. So usually when we're talking about the system, we're talking about the actual reaction itself. The surroundings is everything else. So for example, if we have a typical chemical system, the contents of the flask is the system. So the aqueous solution, when we're doing a titration, for example, the solution itself is the system. Everything else, including the container, right? Including the Erlenmeyer flask, including the air around it, including the bench that it's sitting on, including the room that it's in, that is all the surroundings. So in principle, everything else in the universe is the surroundings. But to be fair, what happens in the lab isn't really going to affect anything about what's happening on Mars. So we only really care about the relevant surroundings. So here we are again with our second law of thermodynamics. The entropy of the universe increases for a spontaneous process. So we can talk about two different types of processes, one that's more theoretical and one that's actually real world. So a spontaneous process in an isolated system, the delta S of the system has to be greater than 0 for that reaction to be spontaneous. And if the system is isolated, the surroundings aren't going to change. So an isolated system is something that probably doesn't really exist because there's always going to be some kind of effect on the surroundings. You can't completely isolate a reaction without it affecting the container it's in or some surroundings. Maybe if you were somewhere in deep space doing this, you could get away with it, but for most real life situations, we're not going to have an isolated system. We're going to either have a closed system or an open system. So both of these types of systems can interact with the surroundings, right? So if you have a container and there's an exothermic reaction, if you touch that container, obviously you're going to feel some of that heat, and that's because the heat is heating up the container, it's heating up the air around it, it's heating up your hand. So that reaction is definitely affecting the surroundings. So for a spontaneous reaction in a closed or open system, which again, practically every system everywhere, the delta S of the system plus the delta S of the surroundings, so the entropy of the system plus the entropy of the surroundings, must be greater than 0. If delta S is less than 0, then the reaction is not spontaneous. So here we are back with our cold pack, and we know that this is an endothermic process, so heat is lost by the surroundings, so the heat is going into the system. So if heat is lost by the surroundings, that means the temperature of the surroundings is decreasing, and if the surrounding temperature is decreasing, that means the entropy or the disorder must be decreasing. You can think of this as it's getting closer and closer to a condensed phase. So if we had gas that was at a specific temperature and we cool it down, at some point it's going to turn into a liquid. And a liquid is more ordered than a gas, and a solid is more ordered than a liquid. So in this case, the delta S of the surroundings is going to be less than 0. But since the system turned from something that is a crystalline solid to an aqueous phase, that is increasing the disorder of the system, resulting in the delta S being greater than 0. Increased freedom of movement of dissolved ions results in more disorder. So the net change in the entropy of the universe in this case is greater than 0 because the system is gaining so much entropy by the fact that it is changing from a solid state into aqueous ions. So this is why this particular reaction is spontaneous. It doesn't have to do so much with the movement of heat. It has more to do with the increase in molecular motion between the solid phase and the aqueous phase. So when we're looking at the second law of thermodynamics and trying to determine whether or not a reaction will be spontaneous or not, we need to know the signs and the magnitude of both the delta S of the system and the delta S of the surroundings. So if both the delta S of the system and the delta S of the surroundings are positive, then the delta S of the universe must also be positive. Now, if both the delta S of the surroundings and the delta S of the system are negative, then of course we're going to have a negative delta S of the universe. So in the case of them both being positive, we're going to have a spontaneous reaction. In the case that delta S of the system and delta S of the surroundings are both negative, then we're going to have a non-spontaneous process. Now, if we have one of delta S of the system being positive and the other being negative, then the magnitude of each of those components matters, right? So if we have a situation where the delta S of the system is a little bit negative, but the delta S of the surroundings is quite positive, then the overall delta S of the universe, in this case, can be positive. But if our delta S of the system is very negative, and the delta S of the surroundings is less positive than the delta S of the system is negative, then the overall delta S of the universe in this case is going to be negative. So we can use the same argument in this slide as we did in the previous slide to justify whether or not the reaction is going to be spontaneous based on the sign of delta S of the universe being positive or negative. So let's talk a little bit about entropy and temperature. So processes usually occur with some kind of transfer of energy. So there's going to be some energy that is being consumed by the system or released by the system. But we can also talk about processes that are isothermal. So this is a process that occurs at a constant temperature. And we can talk about reversible processes, which are processes that can run in both the forward and reverse direction with no net heat flow in or out of the system. So that just basically means that The forward reaction, for example, say releases some heat, but the reverse reaction would consume just as much heat as was released by the forward reaction. Now, for this to be true, we can only really talk about really tiny amounts of heat flowing in or out of the system. It doesn't really work for large amounts of heat. So for an isothermal process, the delta S of the system equals the heat of the system divided by the temperature in Kelvin. So Q reversible is the flow of heat for a reversible process. So Q can be either positive or negative. Positive meaning that that particular system is gaining heat, negative meaning that particular system is losing heat. So if we consider an ice cube melting at 0 degrees Celsius on a countertop which is at room temperature. In this case, we consider the ice cube to be the system because that is the part of the universe that we are looking at or studying. So heat flowing into the ice cube results in a Q system being positive, right? Because heat is flowing into something, that results in a positive Q. And we know the temperature of the ice cube being 273 Kelvin or 0 degrees Celsius. So we can determine what the delta S of the system is because we know from the question what the Q for water is. Now heat flowing out of the countertop in this case is the surroundings. So delta S of the surroundings is going to be negative Q of the surroundings. So heat being lost by the surroundings, so that's going to be a negative Q. And we know the heat or the temperature of the countertop being room temperature. So now we have a number for the delta S of the system and the delta S of the surroundings. We can plug that into our second law of thermodynamics. So this is delta S of the universe equals the delta S of the system plus the delta S of the surroundings. And if we run through the math in this question, we end up getting a positive number. So this shows that thermodynamically, the process of melting ice at room temperature is spontaneous because the delta S of the universe is positive. We could also look at this in terms of those arrow diagrams that we saw a couple slides ago. So the delta S of the system, plus 22. So here's our plus 22 for our delta S of the system. The delta S of the surroundings is negative. Okay, so here's our delta S of the surroundings. But the delta S of the surroundings is less negative than the delta S of the system is positive. So when we add those numbers together, we still get a little tiny positive number for the delta S of the universe. Again, since the delta S of the universe is positive, that means that this reaction is spontaneous. So this table just shows you under what conditions a reaction is always spontaneous, always non-spontaneous, or depending on the magnitude of delta S system and delta S surroundings, whether the reaction or process would be spontaneous or non-spontaneous. So a few slides ago, I briefly mentioned that entropy is related to temperature. So when we were talking about the ice pack, once the ice pack has been activated, the components inside cracked and the reaction occurring, then the surroundings are cooling down. Cooling down a gas or a liquid or a solid even reduces the entropy of that system. And the reason it does that is because it is changing the kinetic energy of the molecules that are part of the surroundings or part of the system, whatever one we're looking at. Okay, so if we increase the temperature, that increases kinetic energy, that results in more molecular motion, more translational motion, more rotational motion, more vibrational motion, and that results in more entropy. Decreasing the temperature has the opposite effect, resulting in a decrease in entropy. So the last point here I have will help take us into the next section. At what temperature does all molecular motion cease and entropy equal 0? The quick answer to that is at absolute 0 or 0 Kelvin. That's all I have for this section. If you have any questions, feel free to ask.